Hi, thank you for joining us today for one of Transcat's exclusive on-demand webinars, Uncertainty Measurements. My name is Sarah Wallace from Transcat, and joining me today is Ken Kolb, our presenter. He's Transcat's metrology engineer. Ken has over 30 years experience in metrology, with 2 of those years being with Transcat. Though this is an on-demand webinar, we still encourage you to send us any questions that you may have through transcat.com on the Contact Us page, and just reference the webinar that you're listening to today. So with that, I will pass it on to Ken for our webinar.
Hi. In this presentation, I will discuss estimating uncertainties in measurement and calibration. First question, what is measurement uncertainty? Simply put, measurement uncertainty is an appraisal of the reliability of a measurement result. I will describe a methodical approach that addresses both simple and more complex cases. There are many application examples, some practical everyday domestic events, and there are applications in assembly and manufacturing plants. And there are also technical requirements for traceability, such as with the calibration laboratory in Transcat, but also after the calibration we perform, propagating the traceability further down the chain. First, a simplistic example. Perhaps this morning you went out to your car and you noticed one of the tires looked a bit low, and of course the radial tires can be a little deceptive. So you check the pressure with your tire gauge, and it indicates 31 psi. But what is the real pressure in the tire? To answer that question, we need to account for the fact that the tire gauge itself may have an error. For example, when it indicates 31, perhaps it's only 30, or maybe it's 32. There are also repeatability limitations. If you use the tire gauge 5 times, you might get 5 slightly different readings. Some of that is due to limitations of the tire gauge itself. Other influences might be the technique. If you hold the tire gauge at some slight angle, not make a good contact with the valve stem, the reading could be off that way. So this is kind of a simplistic example of an uncertainty assessment for an everyday event tire pressure. But there are other everyday examples as well. When you buy meat at the superstore or the supermarket, you assume that the markings are correct so that you're paying the right amount. Likewise, when you fill up the gas tank at the gas station. And of course, we hope that the speedometer in the car is right so that we don't get a ticket for speeding. Next, I would like to describe a more complex case, a manufacturing example. It's actually a composite of several real cases that I have encountered through the years. In this example, a manufacturer produces a high accuracy pressure calibrator that it distributes around the world. It has this company has multiple subsidiary locations around the world that stock these items for quicker delivery to the customer. And just prior to delivery, they perform a final accuracy check of this instrument. The problem is that during this final verification test, they had a very high reject rate. The second problem is that after implementing numerous solutions to try and solve this problem, none of these solutions seem to be effective. These included stricter controls on the manufacturing process, introducing intermediate checks along the way. It even included product redesign and changes to the packaging and shipping, but none of this was effective. Perhaps that seems familiar to some of you if you work in a manufacturing environment. So the engineers took a closer look at the process. They recognized that the accuracy of this pressure indicator requires the use of a deadweight tester for the final verification. And evaluation of the uncertainty of this deadweight tester and the application indicated that the deadweight tester should give good results, but the uncertainty evaluation also showed that if the deadweight tester was malfunctioning or was operated incorrectly, the errors could be similar to those found during the pre-delivery verification. So the engineers conducted audits of these subsidiary locations, found that indeed the procedures and the techniques and the operating methods varied widely, and that this was likely the source of the repeated failures during this final verification process. Some locations operated the deadweight tester incorrectly. Others made erroneous corrections for some of the key influences. Local gravity, for example, air buoyancy, temperature, height corrections. So the problem was solved. The uncertainty evaluation helped reveal the shortcomings in the product stream, and those led to improvements in the product and in efficiency in the process. A lesson learned from this is that if the manufacturer had conducted this uncertainty review in the beginning, they may have saved a lot of costly rework and delays in delivering product to the customer. So then, what is involved in performing this uncertainty evaluation? Is there a guide? Are there examples? How do we get started? Well, before we get started, it's somewhat of a technical exercise that involves a number of special terms and statistical concepts, so I would like to review some of those first. First on the list is the term accuracy. What does that mean? Actually, it means different things to different people, but it is a qualitative representation of the capability of a tool, an instrument, or an indicator. As we will see later in the presentation, the definition of this term evolved a bit through the years, where some would try to enhance the clarity of this term by using relative accuracy or absolute accuracy. And I think these only go to show that there are limitations in the meaning of this term. It means different things to different people. In general, relative accuracy is the limitation of the performance of this device or mechanism, generally what we call performance or precision, as we'll talk about in a minute. And then the absolute accuracy, as it was used some years past, corresponds more closely to what we call today measurement uncertainty. So it can be very confusing, and when we speak in technical terms about these, about uncertainty, we try to avoid the term accuracy except in general conversation. As an illustration of the qualitative nature of this term accuracy, perhaps we can look at a cup of coffee. So the qualitative description would be perhaps a tall serving cup. Of course, it's robust and flavorful, served hot and frothy. Those are nice marketing descriptions, but don't really tell us anything other than perhaps a perception that maybe it's taller than the competitor or better flavor. The quantitative description, more like product specification performance, might give more specifics, like this 7-inch tall serving cup or 12 ounces or served at 150 degrees. Won't talk about the cost. So then moving on to the more technical terms that we will deal with, identifying the contributions from instrumentation and process and so forth. Precision. Some refer to this as performance. We're talking about the capabilities of an instrument or a system. More specifically, linearity, repeatability, hysteresis, temperature compensation, long-term stability, things like this. When we conduct calibration, we make measurements of the characteristics of this item under test, and often have to make an assessment about whether it conforms to specifications or not. And one of those specifications is, of course, linearity. Unfortunately, there are several definitions of linearity depending on the type of sensor and the manufacturer and so forth. And in this slide, there are three designations. At first glance, they may look very similar, but upon close inspection, if you look at the dashed line showing a trend, a straight line trend through each of the curves, you'll see they are a little bit different. On the left side, labeled best fit, some call this a best fit straight line, in some specifications BSFL. In the kind of a summary representation of the response of the test instrument, it's a trend through the data, does not correspond to any particular point along the way. It's only a best straight line fit. In the middle section, this trend line is fixed at 0, and then the slope of that line is adjusted to match the remaining points, kind of an average of the rest of the pattern. And then the third section, terminal point, that has a fixed point both at the 0 end and at full scale. Generally speaking, the terminal point nonlinearity specification applies to higher performance devices and the best fit straight line to lesser performance, but not necessarily the case. In this example, it's only here to illustrate that there are differences. There was one case I was involved in where an OEM transducer that had specifications for conformance according to the best fit straight line, as shown on the left, was incorporated into an instrument where the instrument specification was based on terminal point. So during the manufacture of this product, some quantity of those instruments would fail the linearity test according to the terminal point specification, but they would pass according to the best fit specification, so they could not be used in the instrument, but they also could not be returned to the OEM for warranty because of this difference in the specification for linearity. Along with linearity, many transducers have other response characteristics, such as repeatability and hysteresis. So this chart has the same general shape as the ones we looked at, but it also includes 3 sets of data superimposed on top of each other. You can see that from the a somewhat closely spaced group of 3 upscale calibration curves and then 3 more curves downscale. And what this represents is the combined effect of repeatability and hysteresis. The upscale and downscale, if you can imagine an average of each of those 2 patterns, that offset between increasing and decreasing is the hysteresis. There are different definitions depending on the manufacturer of the item. Perhaps it's a peak-to-peak hysteresis specification, which would be the difference between the average upscale and downscale, or it may be plus or minus specification. And then for the repeatability, this assessment would be made based on repeatability, the scatter of the readings within each of the same type group. So, for example, the upscale readings would be evaluated looking at the difference between those 3 runs, and independently, the downscale readings would be evaluated. So these are characteristics that often have to be evaluated to assess the conformance of a test instrument during calibration. They also may be contributing factors to the uncertainty assessment as we pass our knowledge of a measurand down the chain of traceability, which leads to the next topic, traceability. What is traceability? There are 2 subtopics here, a defined path of traceability and a defined uncertainty. So let's talk about that in a little more detail. In some years past, the definition of traceability was limited to this concept that a measurement at the end of the chain was traceable if you could demonstrate an unbroken chain of comparisons to the top level. In this diagram, the upper left-hand side that's labeled NIST. In fact, the description at that time was typically traceability to NIST. In the modern terminology, we don't think of it as traceable to NIST. We describe it as traceable to the SI being the International System of Units, actually maintained in France. So we say it's traceable to the SI through NIST, typically through NIST, not essential to be traceable through NIST, but commonly it is the case. So in this diagram, the traceability is through NIST. It goes through a series of items, instruments or systems, ending in the bottom right-hand corner with the pressure measurement that we make out on the shop floor somewhere. So that diagram would be characteristic of the earlier definition of traceability, but the modern definition of traceability also includes the requirement that we have a stated uncertainty at each of those levels. So now we can see at the top level, it is a very low uncertainty, 0.000 something, and as we move down the chain to the right, that uncertainty value increases. Moving on to the uncertainty, the first item under uncertainty is ISO and RSS. In this discussion, ISO generally refers to a method. It's referring to an ISO document called the Guide to the Expression of Uncertainty in Measurement. So when this method is applied, it's often generically referred to as the ISO method. Some also refer to it as the RSS method, RSS being an acronym for root sum of squares. So in this ISO method, it is a rather technical process that is based on statistics. So we need to have a common ground on some of the basic statistical concepts. So I will review a few of those. Standard deviation. This is a statistical tool for expressing the spread in the values about an average for a group of repeated measurements. So if we measure some parameter, perhaps the length of a table, if we measure that length 10 times and get 10 similar but different values, we can assess the difference between each of those values and the average and compute standard deviation, and that gives us a statistical index of the range of values that we might attribute to that type of measurement. It is an uncertainty component for that particular measurement. And under certain circumstances, the meaningfulness of that is fairly straightforward in that if we use that single standard deviation, it will encompass about 65% of similar measurements, meaning that if this standard deviation is 1, 65% of similar measurements would be within plus or minus 1 of that average. If we double that to 2 standard deviations, now we have 2, then it would encompass about 95%. So 95 out of 100 similar measurements would fall within 2 of that average. In the uncertainty analysis process, many of the uncertainties will come from sources other than this repeatability example that I made. And when we combine these different uncertainty components together, the ISO guide directs us to adjust each of these to what's called the equivalent standard uncertainty. For a repeated measurement such as the length of the table, that corresponds in general to the single standard deviation. If it's from some other source, specification, or some other type of reference, finding the equivalent standard uncertainty may be a little bit more complicated. Some other things have to be considered. For example, the frequency distribution. There are different signatures to the range of values that are attributed to the different values that might come from a measurement. And the way that those different values are arranged has some impact on the statistical tools that we apply to account for those properly. The next on the list is the sensitivity coefficient. In some measurement systems, there are a multitude of influences, most of which commonly have different units of measure. If we are trying to assess how each of those impacts the final measure end, we need to essentially convert those all to the same unit of measure, and that's the purpose of the sensitivity coefficient. So from these steps, we can identify an uncertainty influence for each parameter. Then we combine these different parameters together, generally using root sum of squares. There are some constraints about that we'll talk about later. And then the final step in this ISO recommended method is to expand that from the approximate 65% level back up to about 95%, typically by multiplying by 2, often referred to as K factor of 2, K equals 2, or coverage factor is equal to 2. So this international recommendation that I'm referring to is the ISO guide. It's a very formal procedure, certainly applicable to advanced evaluations or when accreditation is involved, but there are other simpler general purpose applications where it may be overkill, so there are simpler methods we'll talk about later also. The ISO document that I've been referring to is the Guide to the Expression of Uncertainty in Measurement, a fairly long name, thus the common approach just referring to it as ISO. This is my summary of the key steps in the process following the ISO guide. We need to identify what the sources of uncertainty are in the particular measurement process we're evaluating and estimate a magnitude of influence for each of those parameters. To do that, sometimes it helps to understand the overall process. Of course, we need to know the details of the specific instrument, but it helps to sometimes have an overall perspective. So I'm going back to this traceability diagram. In this diagram, each circle represents an instrument or a system, a collection of instruments, and each of those has identifiable characteristics, performance limitations, linearity, repeatability, hysteresis, like that we spoke of a minute ago. Those represent a limitation at each respective level in the process and contribute to the errors that accumulate as you move down the chain. In addition to that, however, there are lines connecting each of these circles, and those lines represent a measurement process. There's a measurement involved each time we transfer from one standard, from one artifact to another, from a standard to a test item. And in that measurement process, there are typically additional uncertainty influences from environment, from procedure, from technique. And all of those accumulate as we move down the chain. So how do we find the parameters? One place to look is the specifications from the manufacturer. Sometimes they're pretty straightforward. Other times you have to dig a little bit. But here's an example for a digital pressure calibrator, somewhat like in the example I made earlier. So there are some key specifications here summarized over to the right. Precision, this is the combined effect of linearity, repeatability, hysteresis, and such like that. But it does not include the long-term stability. That's a separately stated term, also shown to the right. So that represents the performance of the instrument. It does not include the uncertainties that accumulate in the chain that leads to the standard that's used to evaluate this device. For example, in the lower right-hand, just below the middle of the slide, there's a circle that says user 7215XI. That placeholder is representative of the instrument that we just looked at. And above and to the left of there is the chain that supplies traceability during the calibration of that digital pressure controller. Referring back to the specifications, the technical information from the manufacturer of this device, there's additional information that tries to account for the uncertainty in the traceability, and as well includes allowances for degradation of the performance over time, a drift allowance. And again, from the specifications, we can see more detail about how this comes about. For example, the precision number is listed as 0.005% of reading. Long-term stability allowance for 1 year, 0.0075% of reading. Calibration standard. This is an uncertainty in the parent standard that represents that upper part of the chain that we just talked about. And a few other ancillary items that might be important to a measurement process if you use this tool in your calibration. So then, if we want to use this device as a reference, if the calibration standard that was used has the level of uncertainty that's allowed in this example uncertainty budget, then it's reasonable, then this representation of the uncertainty is a reasonable assessment. But if the calibration standard that's used has significantly larger uncertainty than this, then the final uncertainty in the usage of this device will be higher as well. Next on the list of considerations in the uncertainty analysis is identifying the type of distribution, so we'll talk about what those are. Referring back to the example of measuring the length of the table, if we measured that table 100 times, we get 100 different but fairly closely spaced values. If we average those 100 readings and then subtract that average from each of the individual readings, we'll find that those differences tend to fall pretty close to the average, and the further away from the average that we go, the fewer measurements fall in that category. So if we count those in bins, as it's called, small increment deviations from the average, and plot those in a bar graph form, we might see something that looks like this chart, a bar graph. And the significance of that is that if we have enough readings and the distribution of those readings is normal, then this bar graph has similar appearance to the Gaussian curve depicted in the bottom right, labeled normal distribution. And the importance of that is that this standard deviation of the scatter about that average has statistical significance in that if you look at this curve in the bottom right-hand side, there's a middle marking that says 100. We can consider that the average. And then a dark shaded area that covers an interval from -1 standard deviation to +1 standard deviation. And that darkly shaded area would encompass about 68% of 68 out of 100 measurements made under those conditions. Simply doubling that standard deviation, now we encompass, making it twice as wide, encompasses about 95%. So that's where the simple statistical numbers come from, doubling or dividing by 2 when we try to estimate different coverages. It is based on having this normally distributed variable. But there are different distribution types, and this ISO guide lists 3 of them. Of course, normal distribution. It also lists triangle distribution and then rectangle distribution. I'm not aware of any specific cases that necessarily use triangle distribution, but there are several common cases where rectangle distribution is appropriate or commonly applied. One of those has to do with the resolution of a digital indicator. I believe I have an example of that coming up. We'll get to that in a minute. The significance of these different distribution types, though, has to do with how we identify the equivalent standard uncertainty before we combine these different parameters together. If, for example, the uncertainty parameter that we're considering is directly from the statistical evaluation of the repeats of this measurement to the length of the table, then that would fall in the upper category. If that number is stated at 95%, then we simply divide by 2 to get the standard uncertainty. If the parameter that we're evaluating is believed to have a triangle distribution, and we have the limits, the upper limit and the lower limit identified, then the equivalent standard uncertainty is found by dividing that upper limit, or dividing that limit by the square root of 6, which is about 2.45. And then for the rectangular distribution, this limit designated A in the diagram, this limit A is divided by the square root of 3, which is approximately 1.7, to find the equivalent standard uncertainty. So there's a kind of a quick overview there showing what the difference is. The normal distribution getting from a 95% number to a 65% number, we divide by 2. In rectangular distribution, we divide by 1.73. So that's why it's important to identify the distribution of these different influences so that we can find the correct standard uncertainty. So again, the applicability of these different types, and of course there are a multitude of other types, but for these 3 identified in the ISO guide, there are many measurement influences that fall into this category of normal distribution. The vast majority of repeatability measurements, a large portion of instrument specifications, calibration, traceability, uncertainty typically has this kind of distribution. For triangle distribution, it's a much more crude assessment, typically used only when very limited data is available, but you still need to make an assessment. More of a design tool. And then rectangular distribution, the common examples of that would be instrument resolution, particularly in an numeric display, or a graduated dial. And then another common implementation for this type of distribution is for manufacturer specifications that have a generic kind of specification where they're not stated as having a particular coverage interval, for example. We'll come back to that in a minute. So here are a couple of examples in the upper left-hand corner, a section of a dial gauge with a pointer. If you look closely, you can see that it's not pointing directly at one of the graduations. So the question always comes up, how many times can you, how many segments can you divide each graduation into? Some will say that it's only good to one increment. I know from experience that in some cases, depending on the quality of the markings and the quality of the pointer and other factors, that it's common to divide graduations into 10 parts. But it's also commonplace that the specifications for the instrument often represent less than half of a division. So if a particular organization is calibrating a gauge like this and their policy is limiting the readability to a single graduation, then that may end up more than double the rating of that instrument. In the upper right-hand corner, a digital display. The image there shows 10.000. If the display is substantially filtered, let's say, and it's a stable reading, that rightmost digit is fairly stable, almost always showing a 0. For the sake of discussion, let's say that's least significant digit. Some refer to that as a count. A change of 1 count would be a change of 1 in that rightmost display position. For that display to move from 10.000 to 10.001, you can imagine a value in the next decimal over would have to increase past 5 in that next digit to round off to 10.001. Likewise, it would have to decrease by 5 in that next digit for the display to round down to 9.999. So there is a range of plus or minus 1/2 of the least significant digit, 1/2 of a count, plus or minus. And over that range of plus or minus half a count, we don't have any way to determine where within that range the actual value is. And that is the definition of rectangular distribution. The other application where rectangular distribution is commonly used is the specifications for an instrument. We looked at specifications for a pressure device earlier. Those specifications in the fine print somewhere, it states that those have 95% level of confidence, or perhaps it says K = 2 or something to that effect. That being the case, those would be treated as having normal distribution, whereas if the specification is more generic and doesn't indicate some coverage interval, 95% or 99%, or it's just a generic specification, then at Transcat we would assign the rectangular distribution. As we accumulate this list of influences, it is likely that some of these will have different engineering units, different units of measure, and we'll have to account for that before we combine those into a composite representation of the process. So the example I was talking about previously was pressure. The definition of pressure is a fairly simple formula, particularly as it relates to mechanical devices, a deadweight tester, for example, at least on the surface. But when we put it into practice, it evolves into a host of different parameters that have to be accounted for. So here's a formula that includes variables to account for mass, acceleration of gravity, density of air, temperature, height corrections, and such. So all of these parameters, of course, are uncertainty contributors, and the uncertainty in each of those will be at their own respective units of measure. For example, the uncertainty in height would be in inches or centimeters or millimeters. The uncertainty in mass might be in grams or kilograms or pounds. The uncertainty in air density, perhaps grams per cubic centimeter. And we need to translate all of those to a common unit of measure, pressure in this case, before we can combine those together. The ISO guide gives us a tool for doing that called the sensitivity coefficient, and it says we can apply this model function equation to make an estimate of the sensitivity of each of these parameters. If your calculus is as rusty as mine, you might also be able to apply the experimental method, which will work in the majority of cases. And the way we apply this one is, if you look at the formula, we insert an appropriate value for each of these variables, and in this case, compute a pressure. Then for the parameter that we are investigating, mass, for example, we change that mass value by an amount that corresponds to the uncertainty in that mass. That will result in a different pressure, and that change in pressure is a direct result of the uncertainty in mass. So basically, we let this formula convert that for us. Okay, back to the pressure indicator. Are there mixed units of measure with the pressure calibrator? Well, certainly there are. For the laboratory grade instruments, typically a multitude of unit conversions are available. But that typically doesn't affect the uncertainty, assuming that the conversion factors are correct. As it relates to the uncertainty assessment, there's something else that influences the process somewhat like mixed unit, and that is the specification. Specifications may be stated as percent of full scale, or percent of range, or percent of reading. So let's look at that a little bit, see what it means. So here's a graphic representation of a, it says pressure at the bottom, but it could be any indicating device range across the bottom scale, 0 to 100. And on the left-hand side is the contribution from the specification, performance or uncertainty, whatever it may be. In this case, it's 0.003% of full scale being 100. So at 100, the contribution is 0.003. At 50, the contribution is 0.003. At 25, anywhere across the range is 0.003. For percent of reading, in this case 0.005% of reading, at full scale, that value would be 0.005, and it is represented as a straight line from there to 0. So at mid-scale at 50, the contribution is 0.0025. At 0, the contribution is 0. But that's not really practical. It's not realistic. The readings at or near 0 have some performance limitation. So typically there's some lower limit when the specification is based on percent of reading. There will be a lower limit in the form of either a lower limit where this percent of reading no longer holds, or a floor value, maybe a number of least significant digits. In this example, the percent of reading is held down to 25% of full scale, where it becomes a fixed value. Kind of a combination of those other two that we looked at. In some cases, the specification will be either or, for example, 0.005% of reading or 0.003% of full scale, whichever is greater. In other cases, it will be the sum of the proportional term and a floor value, which kind of gives it a little bit of a smooth curve in this region around, as shown in the graph here at 25%. There's a sharp edge there. So in the case where the two terms are additive, or perhaps even combined root sum squared, that won't be as sharp a transition. Not all that big of an impact on the performance, but it does lead to additional complications when you try to combine these different terms together. All right, so this is a representation of of a particular pressure indicator, 0.005% of reading from full scale down to 25%, and then it's fixed contribution below that. And really, it's a plus or minus window, so you can imagine this funnel kind of shape balanced around 0, 0 being the optimum reading. So then this might be a tolerance that we apply when we calibrate a unit under test and perform what we call an as-found calibration before adjustments to assess the condition of it and determine whether it's in tolerance or whether it needs adjustment. So here's an example, and you can see in the upper right-hand corner, there's one that's across the line. The rest of them are marginally below to maybe touching the line. So maybe some of the points exceed the limit, or do they? All right, so I mentioned earlier that there are basic performance specifications. In this case, that 0.005% of reading kind of number. That number does not include the long-term stability, the drift allowance. When the drift allowance is included, now we have a wider band depicted here in blue. So for the as-found reading, assuming that it has been, let's say, 1 year since the last calibration of this device, we actually have a wider band that it can be in before we would say that it doesn't meet the specification, before we say that it's out of tolerance, at least the as-found tolerance. Now, before it goes back into service, it needs to be well within the pink line, kind of the short-term specification. So then, as would normally be the case, this would not be reported as out of tolerance because it meets the specification when we include the drift allowance, but then it's adjusted back much closer to nominal. And that would represent the as-left calibration. Some instruments are bidirectional. They go plus and minus. And this would be an example of one that's plus and minus with the two-part tolerance, percent of reading down to some fraction of full scale, I think 5% in this case. And there are two parts to that funnel, a green one that's the short-term performance and the red that includes a drift allowance. So the as-found readings, the blue boxes, were across the short-term limit but within the drift allowance. So it's operating normally but needs to be adjusted, and then the as-left calibration showed that it was adjusted back to nominal. Another type of sensor might have a specification based on percent of span that would be a fixed value across the range, not that funnel shape that we just looked at. So here's another example, and in this one, on the upper left-hand side, there is one point that's outside of the blue bound, meaning that it exceeds even the drift allowance. So that one would be stated as out of tolerance. And then it was adjusted, normalized back to nominal. All right, so for these different parameters, we need to assess, we need to account for the units of measure and adjust each of those to the appropriate value so that we're working all in the same unit of measure. And that gives us the uncertainty, the standard uncertainty for each of those components. Once we have that, we can combine those to represent the combined uncertainty in the process. And that combination is generally root sum of squares. But that root sum square combination is dependent on those uncertainty influences being independent, not related to each other. An example of this is at least an example of the impact that this has. fairly simplistic case, let's say that there are 4 uncertainty influences that we're considering. They are independent from each other. One does influence A doesn't influence B or C or D. But in this example, each of them has a 1% contribution to the uncertainty. So the simplistic assessment of this might just be adding those 4 1% terms together, and it might seem that the uncertainty would be 4%. And while it is possible that the error could be 4%, it's actually rather unlikely that all of those components would be at the 1% limit and all in the same direction. It's probable that they would have varying degrees of error within that 1%. Some would be plus, some would be minus. So there's a statistical technique for combining those, basically this root sum of squares term, that gives us a probable limit of error. So while it's possible that the error could be 4%, it's probable that that's limited to 2%. And if these 1% values assigned to the 4 influences are stated at 95%, then this probable limit of 2% is also a 95% level of confidence. Again, this combination by root sum of squares depends on these influence parameters being independent, not correlated. And that's not always the case. There are some correlations that we encounter. One of those has to do with the deadweight tester that we talked about a minute ago. A typical deadweight tester uses weights, masses if you prefer. So this is an example of a table of mass values. The mass values are reported, and for each of those mass values, an uncertainty is stated. So if we used 10 of those pieces, could we not just combine the uncertainty of those 10 pieces root sum square? Let's look at a picture of a deadweight tester. You can see the weights, the disc-shaped platters stacked on there, and the smaller pieces at the top, and I don't know, maybe 8 or 10 larger platters at the bottom, all nominally the same. In this case, they happen to be about 5 kilos each. Since they are the same denomination, it is probable that they were each calibrated using the same 5-kilogram standard. There is an error in that 5-kilogram standard, and that error is passed on equally to each of these 5-kilo deadweight tester weights. So there's a systematic error in those. Some portion of the uncertainty in each of those 5-kilo masses is correlated with the uncertainty in the others. Because we don't know how much of that is correlated, it's customary to treat the entire weight set as being correlated and simply add the uncertainties together rather than combine root sum square. Continuing on, complexities, I guess, in identifying certain parameters, particularly as it relates to standards that might be used in the laboratory that maybe don't have specifications, or you're trying to qualify a system to make sure that it meets specifications. One of those specifications being long-term stability or drift. This chart is an example of the comparison between 2 laboratory standards over the course of about 10 years. And over that period of time, the trend in this data is very, very close to 0. You may be able to see a fine dotted line, and that dotted line is indicative of the the slope of that line representing a drift rate of 0.07 parts per million per year. It's really not statistically significant because you can see there's a lot of up and down in the data, scatter in the data, and that's because of the repeatability limitation of this process. The repeatability of this process is orders of magnitude larger than the parameter that we're trying to measure, stability. So to quantify the stability when the value is below the repeatability of the process, you have to either take a very, very large number of readings or extend the readings over a long period of time, and that's the case here. Because if you only have a few readings over a relatively short period of time, as you can see at different points along the scale here, like right near the middle, there may be several readings closely spaced in time that appear to have a pretty high trend. But that's just the nature, the random nature of things. They happen to align that way. It's not drifting that way and then drifting back the other way. It's just a limitation of the measurement process. Another example of similar instruments, but in this case, there is a significant trend versus time. The slope of that dotted line is about 11 parts per million per year. So we might consider using that value. We have evidence for this particular tool that we're using as a standard, perhaps. But there's a lot of scatter about that line, some up and down motion. So there's some uncertainty in that 11 parts per million per year that should be accounted for. Perhaps the value that we would use in this case is more like 20 parts per million per year. All right, so here's a summary list of the common uncertainty sources. Some of these are more like categories. For example, in the upper left-hand side, the standard of the system has performance limitations such as linearity, repeatability, hysteresis. There may be others particular to a certain instrument type. Drift, traceability, those are the main things we've talked about so far. Below that is reproducibility. It's kind of the big brother of repeatability. That includes not just the repeatability of the measurement, but changing conditions or different technicians. And that's affected by training and technique in the equipment that you're using and the resolution of the device under test. On the right-hand side, there's a list of influences that can have an impact. Not that they do in every case, but sometimes they can be significant. So it's more of a reminder to look for these. Software, data acquisition limitations, engineering units conversion. If you don't use the right conversion factor, there can be an error. Filtering and signal conditioning, that can lead to complications as well. And then down below, group labeled as environmental influences. Some instrumentation is largely immune to common environmental changes. Other instruments, the deadweight tester, for example, is very highly dependent on the environment. And then a note at the bottom, this list of influences does not include human errors, also called gross errors. I think in many cases we couldn't make the uncertainty budget large enough to account for those. We make a lot of large mistakes. Fortunately, most of those are large enough that it's obvious in the data, and we recognize the mistake and make remedy before we have a faulty reading. All right, so here's an example of an uncertainty budget, as we call it. This is a screenshot from a spreadsheet, such as Microsoft Excel, a nice tool for tabulating these different influences. And this is called an uncertainty budget because it is an allowance for various different parameters, so that we don't have to make this uncertainty calculation every time we make a measurement. If in the budget we have an allowance for certain parameters, and then when we operate the system, we maintain controls to the process to ensure that this parameter and that parameter are within the budgeted values, then this uncertainty budget, expanded uncertainty, is considered representative of that process. So there are several sections to this. The upper section is general information, what it is we're measuring, the equipment involved. In the middle part, there are two sections, Type A and Type B. Type A uncertainty generically is an uncertainty that comes from statistical assessments, such as the repeatability and the length of the table we were talking about measuring. And Type B is everything else, specifications from a manufacturer, the traceability uncertainty that comes from the standard. And then at the bottom, the combination of those and the final value is the expanded uncertainty. So going across the columns that are in the middle, there's a description of the parameter that we're including in the Type A section, that's repeatability. In Type B, below there is manufacturing specifications, and below that, the calibration uncertainty. So in this case, those are separately listed items because the review of the manufacturer's specifications either did not include the calibration uncertainty, or the amount that was allowed for in there was not a good match to the uncertainty in the actual calibration of this tool. And in the repeatability section above there, this is not the repeatability of the standard that was used, it's the repeatability of the process. It includes the standard, it includes the technique, the training, the procedure, and to some extent the resolution and readability of the device under test. So then going across the page, we have the uncertainty value for each of those. Then we have the units, and you can see here that the units are the same for all of these. We do that intentionally to avoid the complication of computing sensitivity coefficients in this table. We simply make sure that all the uncertainty values that go in here are in the same units of measure. In this case, microvolts per volt. And that allows us to use the sensitivity coefficient of 1. Continuing across the page is the distribution type, normal distribution for the repeatability. The manufacturer's specification is listed as rectangle distribution. And 2 columns to the right of there is the divisor, 1.73. That's the number we talked about before, 1 over the square root of 3. And between those 2 columns is one with the heading DEG, that's short for degrees, which is short for degrees of freedom. Degrees of freedom has to do with the reliability of the standard deviation at predicting the population standard deviation. When we measured this table length, for example, maybe we had 100 observations, or maybe we only had 10. The fewer samples that you have that go into this computation of the standard deviation, the lower the reliability of that standard deviation at predicting the real case. The real case being what's called the population standard deviation, which would include everything. Obviously, we can't measure an infinite number of times. It's limited, but there's a statistical tool for accounting for compensating for that diminished sample size, and that is the tau distribution, sometimes called T distribution or student T. And it's a correction that we apply based on the sample size, actually the degrees of freedom. And the degrees of freedom is really fairly simple. It's the number of observations minus the number of coefficients that we take from that data set. For example, if we measure some parameter, we have 15 measurements and we use a simple average, that simple average is one coefficient that we're taking from that data, one coefficient to represent kind of the average of the group. So then 15 readings minus one, one coefficient that we're taking from that data leaves 14 degrees of freedom. So then, if we look to the statistical reference guide and find the student T table, we can find the appropriate multiplication factor for, in this case, 14 degrees of freedom, to expand that standard deviation to the appropriate 2 sigma level, meaning 95% or approximately 95%. So from this single standard deviation, instead of multiplying by 2 to get 95%, we have to multiply by 2.2 because of the relatively small sample size of 15 data points. Another example is determining a best fit straight line from 6 observations. So this best fit straight line gives us 2 coefficients, a slope and an offset. So from these 6 observations, we're taking 2 coefficients, so 6 minus 2 is 4 degrees of freedom. So then the sample standard deviation with 4 degrees of freedom is expanded to the 2 sigma equivalent, the 95% level, by multiplying by 2.87 instead of 2.0. So that's the adjustment factor for a small sample size, degrees of freedom. So sometimes we don't have evidence of the degrees of freedom. We can make a determination about the probable or an approximate degrees of freedom. Most of the specifications that we have are considered to have 100 or higher degrees of freedom. In this table, you can see the repeatability is listed as 100. That's because the student T correction factor was applied. Before applying that student T factor, it would have only 4 degrees of freedom or 14 degrees of freedom, depending on how many measurements were involved. Okay, so continuing on, an alternate approach, or sometimes interwoven in the process that uses the ISO method, we have this category called accuracy ratio. 4-to-1 ratio, TUR, test uncertainty ratio, TAR, test accuracy ratio. What are these? What do they mean? How are they used? What are the guidelines? Why not 3-to-1 or 2-to-1? What's so magical about 4-to-1? Well, first, a description of what these are, and perhaps how they have evolved a little bit through the years. TAR, test accuracy ratio, This is the ratio between the quote-unquote accuracy of the test unit and the standard. But what is meant by this term accuracy? Some years back, the early definition of this was only a comparison of the performance of the standard in the test, performance being linearity, repeatability, hysteresis, like that. It did not include the uncertainty in the standard. The modern definition does or may include the uncertainty, but not necessarily. It depends on the particular organization, their definition of this term. All right, so an example of this, some maybe 25 plus years ago, there was a test item with a rating of 0.003% of full scale. The standard that was used to calibrate it was 0.01%. Well, that's about a 3-to-1 ratio, but it's backwards. However, the performance of the standard, linearity, repeatability, hysteresis, like that, the same parameters that were being assessed on the test instrument, was actually 0.0003%. Actually a 10-to-1 ratio to the test instrument. So in terms of assessing the performance of the test instrument, whether it had sufficient repeatability and linearity and such, that standard was certainly sufficient. But when it comes time to assess the uncertainty in the calibration of that test instrument, the complete uncertainty had to be included. What that means is that the 0.003% rating of the test instrument could not be used to represent its uncertainty. And that's what we try to do with this accuracy ratio business is if you have a high enough ratio between the rating of the test instrument and the uncertainty in the standard, then the rating of the test instrument becomes an adequate representation of the uncertainty in the calibration of that test instrument. So it's often used as a shortcut to the uncertainty process, but that's really not the intent. All right, so because of the variability in the definition of accuracy, the term evolved to test uncertainty ratio, and the early definition of this term compared the accuracy, the rating of the test instrument to the measurement uncertainty of the standard. Perhaps the most common implementation of it these days as well, but there are some who try to make a comparison between the expected uncertainty of the test instrument and the measurement uncertainty. And those two are, to some extent, interrelated. So it's a difficult comparison to make, and it really defeats the purpose of this tool anyway, which was originally a quality control tool to assess adequacy of the standard, not a tool for assessing the uncertainty in the calibration. So it's still a nice tool. There are some benefits if you can maintain a 4-to-1 ratio. It's easier to assess the uncertainty or higher confidence in the results perhaps. But it does not mean that if you don't have a 4-to-1 ratio, it's not a good calibration. It only means that the uncertainty assessment is a little more technical. So then, in the quality programs, let's say, that rely on test uncertainty ratio, when the ratio is 4-to-1 or greater, it's assumed that the uncertainty in the calibration of the device under test is equivalent to its precision rating. And it's easy enough to demonstrate how that's an adequate representation. But what happens if you only have a 3-to-1 ratio or a 2-to-1 ratio? Here's a table to help describe that. On the left-hand side is a representation of the performance of the device under test, the precision, number, linearity, repeatability, etc. Next to that is the uncertainty in the standard, including its precision and its traceability. And there's a ratio between those two of 4-to-1. So then, according to this 4-to-1 test uncertainty ratio guideline, it might be assumed that this 0.01 precision rating of the test instrument is an adequate representation of the uncertainty in its calibration. If we apply the more technical approach, this RSS type, combine the 0.01 and the 0.0025 by root sum square, we get something slightly higher, 0.0103. But that little bit of increase, that 0.0003 increase, is in the majority of cases at or beyond the resolution of the device under test. So it's really not significant. That's why, that's the underlying principle of why 4-to-1 is a good guideline. But if you only have 3-to-1, let's say the uncertainty in the standard is a little bit higher, only 1/3 of the performance rating of the test instrument. We have a 3-to-1 ratio in this test uncertainty ratio guideline kind of policy, quality policy. If that's what you have, it's not uncommon to state that the uncertainty in the device under test is 4 times the uncertainty in the standard. Well, that's not really a fair assessment, although I will say I have encountered that numerous times. It's really a misimplementation of the intent of this ratio guideline. It's not that if you don't have 4-to-1 ratio, the uncertainty is higher. It only means that the ratio type assessment is not an adequate representation of the uncertainty. For example, if we take these two terms, the 0.01 for the device under test and the 0.0033 for the standard, combine those root sum square, we see that it's not tremendously higher than the rating of the device under test, 0.0105. In many cases, that increase of 5 in that last digit is going to be beyond the resolution of the device under test. So again, perhaps not statistically significant. There are indeed some calibration schemes where 3-to-1 is a mandated guideline, not 4-to-1. One of those is high-level mass calibration. So there's not some magic guideline per se about this 4-to-1 ratio. It's a nice tool when it applies, but it doesn't. It has a limit of applicability. As I said before, it's sometimes used as a shortcut for the uncertainty analysis, but it's really not. It is a good guideline for judging adequacy of the standard, which is terminology borrowed from the early mill standard era. The real risk of using this kind of tool is in determination of the in or out of tolerance. In the modern terminology, we might call that probability of conformance. And one of the tools that we might use or method would be guard banding. So going back to this sample of as-found data where we have the pink line that represents the tolerance, we can see the as-found data points are fairly close to that upper limit. One appears to be across the limit. For the sake of discussion, if we consider 4-to-1 test uncertainty ratio and apply simplistic limits as it used to be done in the past, the uncertainty in the standard was considered to consume 25% of the allowance for the test instrument. So then you can see the green line represents a threshold. If it's above that green line, then it would be considered out of tolerance, or at least a candidate for being out of tolerance, because it has to go way up above the red line before we could say definitively that it's definitely out of tolerance. But all of those readings in between would be questionable. But that's the old style, substantially conservative in the modern methods. Even if we have a 4-to-1 test uncertainty ratio, if we apply the statistically based tool of guardband, even the simple guardband limits, you can see the window about that upper limit is much tighter. Let me zoom in on that a little bit so we can see. So we still have the red line at the top that tells us if it's outside of that limit, it is, for all practical purposes, undeniably out of tolerance. If it's at or below the green line, we can say with very high confidence that it is in tolerance. In fact, we can say that it is within the tolerance line with only a 2% risk. All right, so what that does is this point in the upper right-hand corner that's across the red line is clearly out of tolerance, but all of the other readings are definitely in tolerance. And what that does is it limits the risk of recall for the user of this instrument. Whereas if we had reported it based on the simplistic limits of the old style 4-to-1 ratio, all of those would be candidates for potential recall of customer items. And then, just for the sake of curiosity, I compared a simple guardband limit based on a 2-to-1 ratio to the old style limit of a 4-to-1 test uncertainty ratio, and it comes out pretty close to the same. And basically what that means is that even if we only have a 2-to-1 ratio, if the readings are within 75% of the tolerance, there's still a 98% probability that they are within the specified tolerance. All right, so we have looked at where the uncertainty influences come from, characteristics of the instrumentation involved, procedure, technique, repeatability, and these uncertainty contributions accumulate as we go down the chain. And we've looked at the steps involved in how to estimate the uncertainty. Here, generally a summary of the ISO guide. So if you have any questions about this topic, please feel free to contact Transcat, and we will do our best to get you a meaningful answer. Thank you.
Thank you, Ken. That was great. Just like Ken said, we encourage you to ask questions about uncertainties or any other topic that would be of interest to you, or any of the services and products that Transcat offers. You can do so just by going to transcat.com and filling out just the general Contact Us form and just mention this webinar. So thank you for joining us today, and we hope that you found this information on uncertainties useful and applicable to your job. So have a great day. Thanks.